Hi, this is Kian, and in this video I'm back with another linear algebra topic. In this video I'm going to show you how to find the basis for the orthogonal complement given the span, in this case, of a subspace. So we're given a span of W is the column vectors 1, 2, 3, 4, and the vector 1, 5, 6, 7, 8. So first of all, you have to know what the orthogonal complement is. So the basis for orthogonal complement is a set of vectors in which they're all orthonormal, or they are orthogonal to the column vectors that span, in this case, W. So whatever vectors we find for the basis for the orthogonal complement will be in fact orthogonal to these, in which it means that their dot product would be 0. So let's get started. So using several facts and linear algebra facts, we can in fact show that the basis in which the vector, let's say the vectors x, that make up the subspace of the orthogonal complement are in fact the same vectors that also make up the kernel, or the null space, of the transpose of the transformation matrix, in this case A of t. So the transpose of matrix A. So we have to first know what matrix A is. So given the span is a set of linearly independent vectors, we can see that our matrix A is in fact equal to a 4x2 matrix, which is just 1, 2, 3, 4, and then 5, 6, 7, and 8. Now, to find the transpose, what transpose does is just basically switching the orders of columns and rows. So in fact, this is a 4x2 matrix, then the A of t, or transpose of A, would be a 2x4. So in this case, we would have one row that is 1, 5, one column that is 2, 6, one that is 3, 7, one that is 4, 8. And so what we have to do next is to find a kernel. But we know that the kernel of A of t is basically the solution to the homogeneous equation A of t, or the matrix, times the vector x, equaling the 0 vector. I'm going to change colors. Now we know how to solve that. Since we can't really invert this matrix, this is not a square matrix, we have to use the row reduced echelon form. So we have to row reduce this matrix in this form. And in fact, after the row reduced echelon form, or RREF, we go through the process, we will get, so I'm not going to show you all the process, but after doing the row reduced echelon form, you can plug it in your calculator. We get the matrix 1, 0, 0, 1, negative 1, 2. Let me write it here. Negative 1, 2, and negative 2, 3. And then we have 0, 0. So what does this tell us? So this tells us that when we have this equation, this basically two equations we're solving for the unknowns, this basically gives us that based on the RREF, we know that's 1x1, so basically x1, and then we have no x2s here, minus x3 minus 2x4s is in fact equal to 0. Similarly, from the second equation, there's no x1, so x2 plus 2x3 plus 3x4 is equal to 0. Now, since this equation has infinitely many solutions, we can actually introduce parameters. So what I'm going to say is I'm going to let x3 to be t and x4 to be s. And by this definition, x1 becomes x3 plus 2x4, or t plus 2s. And x2 becomes negative 2t minus 3s. And so if you want to basically write our solution sets in terms of kind of two vectors, t and s, we can write it as t times the vector, so the coefficients. So for x1, there's 1. For x2, there's negative 2. For x3 is 1 and then 0. And then you add it. You can factor out an s. For the second vector, you get 2 for x1, negative 3 for x2, 0 for x3, and then 1. And so the kernel is basically the basis of these two column vectors. And in fact, our answer, so basis for the orthogonal complement, would be the basis of these two vectors, 1, negative 2, 1, 0. And in fact, they are linearly independent. They form a basis, so we are good. And just to kind of check our answers, because we initially introduced the fact that the vectors that form the basis for the orthogonal complement have to be orthogonal to the two vectors that we have here as our span of the W. And in fact, if we form the dot product of each of them individually with the 2, we can see that all of them equals 0. And that is our answer. So thanks for watching. I hope you enjoyed this, and goodbye.